That's what interesting. Code events here. Next one is sort of basic. I don't know if we do last thing tonight. I really been on the flow. Yeah, I was like, yeah. Oh. That's it. My syntax was the same as me. Like it was big code that was soft. You thought you could go in the spirit of the UTS stuff. You can still know. So I got to say I don't know. Is that the fight? She got back on. The fact, it's not later. Big on his beard. Okay. Yes, and then all the things on the story. Yeah, but he's honestly. So that is I was. I just I would
Okay. Hello, everyone. I hope you guys are mostly done with the midterm season. So what we discussed last time on the previous 3 lectures was something related to real-time operating systems, which you also do currently in Lab 2 and the project. We discussed the theory, well, scheduling, why do we need it, some of the scheduling algorithms, and we went through some examples. And today's tutorial in the morning kind of give you a couple more examples. My suggestion is try to walk through these examples yourselves, especially the ones in the lecture and the tutorial. If you have any question, let me know, right? And then we can follow up on them, right? What I'm hoping for is that in the last lecture, hopefully in the semester, we would have finished the material already, and I can spare this lecture to, well, take questions and maybe solve more examples related to scheduling. But to be able to, well, leverage this, this lecture and coming tutorials as well, you need to walk through the examples yourselves to see what questions you have, right? So my suggestion is take the tutorial, previous lecture slides, walk through the examples. If you have questions, let me know, let Ali know, let any of the TA knows, and we can help you, okay? So these things are not easy to get unless you really do it yourself. What we're going to cover next is something very related to this scheduling and real-time operating system theory. In fact, one of the reasons why we had the RTOS lectures is exactly for that purpose, for real-time systems, which is we need to basically analyze, let me see. We need to analyze the tasks. Remember in the introductory, are you able to hear me well? Is that okay? Get this a little bit closer. Just let me know if I'm not able to hear. So the reason why we discussed real-time operating system scheduling, or if you remember what even we need an RTOS, general purpose operating system, Linux, for example, or Windows or Android, is we need strict timing guarantees, right? That's the main purpose why people use RTOS in the systems and not something else. Because RTOS is easier to analyze, it's more strict in terms of timing, and it's why it should be used, right? So now, given that we know scheduling, we know RTOS, we need to do the purpose of the RTOS, which is analyzing the task time, right? So be able to guarantee a worst case execution time on the tasks that we have to run. Otherwise, using RTOS is useless, in fact, right? If I'm not able to guarantee this time. So this is what we're going to discuss in today's lecture. So if you remember just quickly, we introduced a task model. Well, the simple one is a periodic task model where every task is being defined by 3 main metrics: D, which is the deadline of the task, C, which is the computation time of the task, or we said this can also represent the worst case execution time, and T is the period. And then we said for every period, the task, we call an instance of the task a job, right? We release a job of that task, and every job is exactly identical. And then the job takes C time to run. For example, this is job tau I0 from task tau I, and then it runs for 3 time units. This is why CI here is 3. And then the deadline is 8 in that case. Then in the next period, a new activation happens, a new job is being released. It takes exactly the same C, which is the worst case, 3 time units. They don't have necessarily to be contiguous or back-to-back, they can be split. Can you give me an example why in one instance those can be really back-to-back, while here the second job has to split them? What do you think? Why this might happen in the end? That's a possibility. Can interrupt happens? Yeah, that's a possibility. What else other than interrupts? What else did we discuss? Yeah.
Like a variable that's stated is in another task.
Yeah, shared. Yeah, what you mean is shared resource in general can be actually another task. That's also a possibility. There is another possibility without shared resources or interrupts. What do you think? Something we discussed in today's morning tutorial. Well, the system is not running a single task, right? So at one point, the scheduler might decide, for example, I'm running EDF, and after running this for one time unit, the scheduler EDF, for example, decides I need to switch to another job, right? So you switch to another job to run it for 2 time units and then come back, right? So maybe you get preempted not by an interrupt or by shared resource, but you get preempted by another task because of the scheduling, right? All of this can happen. But what is important is, or what we guarantee for that task, if this task set is schedulable, is I can finish for every single job all the computation units before the deadline arrives, right? This is the strict requirement that we want to do everything for. If we cannot guarantee this, well, we don't have a real-time embedded system, and there is no guarantees. We cannot really, well, drive the car safely if the airbag is not really guaranteed to be valid, right? Good. So for that purpose, we are going to discuss what we call worst case execution time analysis. So we already modeled the task by deadline, period, computation time. Our condition for guaranteeing the timing requirement is that always, all the time, the worst case computation time or the worst case execution time has to be less than or equal to the deadline, right? Otherwise, again, you lose your requirements, there is no longer guarantees. We can think of this WCET or worst case execution time as an upper bound on the computation time C in the task, right? So that's the worst case instance. The worst possible scenario that this C can run, right? And in fact, there is a whole industry, especially automotive, avionics, etc., into how to obtain this worst case. It's very hard to obtain, right? Good. So just to have a feeling of what does this really mean. So by being able to guarantee this and answering the questions, well, in my car, for example, will my brake-by-wire system actuate the brakes within 1 millisecond? For example, if I hit the brake or it's self-driving cars, so the brake has to be hit by a wire, not by a human. Will this happen within 1 millisecond? Why? Because maybe you have been steady in front of you, right? So this 1 millisecond is going to be your what this 1 millisecond mean? What do you do in our model? What do I call this one? The deadline of the task, right? And then to be able to guarantee or answer this question, you need to calculate WCET, make sure it's less than 1 millisecond, and then if it's less than, then you are good. Otherwise, you need to redesign the system. Another possibility is, for example, maybe if you have a camera-based, self-driving car, steer-by-wire system, can I identify a bicycle crossing within 100 minutes, right? This is basically object detection, right? So you still have a deadline here, 100 milliseconds. Well, basically that's assuming you get raised 10 hertz. But then in a drone, for example, will my drone be able to finish computing control commands? Like, for example, I'm sending a remote command that, well, I need to change direction or, go down, go up, or changing basically all like or whatever control command you are sending to your drone, something similar to what you have been sending through the terminal to our car. Will the drone be able to respond and act upon that command within, for example, 10 milliseconds, or here is 100 100 hertz. Assume that your feedback loop is 100 hertz, right? So all of these are in fact different, representation or different examples of how deadline is important to guarantee in different systems. Think of if the answer of this question, any of this question is no, what's going to happen, right? For example, in a drone, you don't respond within a time, then the command is not being executed, the drone might crash into something and get destroyed or hurt someone, right? Maybe in the car, for example, you hit the bicycle. Well, too bad. Or in the brakes, again, you're able to hit the brake and you go into a wall, right? Or you cross a red line, a red traffic signal, right? So all of these things, the consequences are too bad, right? And this is why we need to guarantee that the deadline under all circumstances, in worst case, is met. How to do it? Well, this is basically the topic of today's lecture. So in worst case execution time analysis, or in general in timing analysis, there are three definitions of an execution time. We have what we call WCET, which is the worst case execution time. This is mainly what a real-time system or a certification-based system is concerned about, because you need to design for the worst case for safety reasons. There is also the best case execution time, and there is the average case execution time. I already told you that safety critical systems care about WCET. Nuclear reactor, a drone, a healthcare system, whatever is the system that is safety critical, care about WCET. Who cares about average case? You give me an example of something that the average execution time matters. We already discussed these things before a few times. Well, laptops you have in front of you right now, right? So you care a lot about response time, right? I want to run as fast as I can. This is your average. If at one point your laptop, takes a lot of time to run one application because it's low in battery or because you are running hundreds of things, so you are playing every day, well, it's okay, right? If you have it once, one big thing. As far as the average case is fine, right? So average case is just general purpose system. And we differentiated between, so in lecture 0 and 1, we put multiple definitions of embedded systems as opposed to general purpose systems. One of them was what metric do you care about? We said mostly embedded systems, especially safety critical ones, care about the WCET, worst case scenario, while average case is more of a concern to the general purpose systems, right? And then we took one step further and said in modern embedded systems, and we give the example of modern automotive, for example, also average cases of importance because we have what we call a mixed criticality. So in the same system, you have, a hard deadline, a hard real-time task, we call it hard real-time. And we also have which is of highest criticality, engine control, airbag, cruise control might be. And then we have also infotainment unit, GPS, reporting or logging tasks. All of these are kind of average case. And they care about average case performance. And the challenge is you need to accommodate for both. Why this is a challenge? Because we also mentioned that in fact, all the techniques we have in systems, modern systems, have a tension or a trade-off between these two. Like most of our laptops are designed for average case, and hence, in fact, they are not good for embedded systems real time. Why? Because we don't have any guarantee, right? In fact, if you run any application in your laptop, there is no strict guarantee that you are going to finish in 1 minute, right? It depends on so many things. What is the status of the operating system? What stability is being deployed, which is not real time? How many other applications are competing with you? What is the power status of the laptop? All of these things creates a huge amount of variability that is not good for real time. So if you design your system for average performance, it hurts a lot the worst case execution time. It hurts analyzability, which is not good for embedded systems. On the other hand, if you design your system strictly for real-time embedded systems, then you care more about the worst case execution time. But on the other hand, your performance will be hurt a little because you have to make design choices that favor this worst case instance. On average case, you might be paying performance penalties, right? And this is again one of the existing problems that is very hot in terms of research and the industry as well, especially again for mixed criticality systems where I need to account for both, right? Good. So one way to visualize these metrics is to look into execution time as some sort of that graph. One question to you to understand what this graph is why execution time might have this variability. So what I'm telling you right now is for one task, exactly the same task or the same application, the execution time is not a single number. I'm not saying, for example, this task will take, well, 1.5 million cycles or 1.5 million nanoseconds. But instead, it will take different execution times at different instances. Why this might be? What do you think? Why do you think a task execution time, C in our task model, is not in fact one number, but instead, well, a spectrum of numbers that we have to count? Yep.
Depend on the environment, if it's the temperature and stuff, and then it's not really.
That's a very nice. Excellent. Yeah, thank you. And this impact of was, I wasn't thinking this when I asked you that question, but that's very valid. So basically, there are also factors that impact, well, the electronics of the system itself, right? Especially in these systems. Think, for example, of those that will go to a spacecraft, right? Which is one of the most heavily certified systems in the system. Like, for example, there are certain FPGAs that has to be hardened, because of hardened industry, that you have to go to space, which means they have to operate without any intervention for a few number of years, usually 10 to 15 years, and you want to make sure that they will not be impacted by being hit by electrons or photons or changing temperature, and then you have to certify them using temperature ranges. Why? Because actually this is being discussed in electronics, but in fact, operating in a certain voltage, like it's not guaranteed for electronics, because based on what temperature you're operating at, if you open, for example, any of the data sheets we have, including the SMU6X, you will find that there is an operational, what we call operational conditions. Like it tells you, I give you this error within this temperature variability, and I give you this error with this temperature variability. Usually it's being tested in labs before the product is being released. So this variability is a factor. Excellent, especially for embedded systems. What else? What do you think? To think of what is this task is in reality, right? Like there is a task that's, for example, in a car, takes data from a camera, has to process it, and then take an action, right? Is there any variability in the example task I gave you? What do you think? Well, this camera is not capturing a constant picture, right? So I'm going into the street, I might be capturing a human being, I might be capturing a tree, I might be capturing a traffic sign. So the input itself, that the task is supposed to process, the input will differ, right? Why this matters? Why you think if I change the input, the execution time of the task might change? Yeah. Exactly, thank you. And can you take this thought a little bit further and say, give me examples from source code, so like statement sequence examples, any other byte, how this might happen within a tool, that if I have different input, I might process it differently based on different things.
Yeah. Example of the camera. If there's like a pedestrian that's a big, has a stationary object, also they need to be more processing for those things.
Yeah, correct. So basically, to generalize that question, or generalize this answer, our programs are mainly composed of what we call control paths, right? So we have if statements, we have for loops and branches, and based on the status of your variables at this one time instance of the application, your if condition might be true or false, right? And then I might take the F or the else, or I might be ending my for loop or continue the iterations, right? So all these things depend on the input, right? And this impacts so many things. It impacts programming, impacts compilers, impacts operating systems, because based on what path I take, well, my application is not in fact one possible flow, right? One possible critical path. It might end up being different paths based on what is the input, right? And being a different path, for example, based on certain condition, I may be calling the function, or maybe based on that exact same condition, if it takes a different value, I call a completely different function. So if I want to analyze how many cycles, how many instructions I'm executing the application, well, I need now to account for these two possibilities, right? Or three possibilities, or 100 possibilities, I don't know, right? And this is why, in fact, timing analysis of code is a very, very hard task to do, right? There are many companies that are specialized only in analyzing software to guarantee execution time. By the way, one of the things that I don't even know on, McMaster is the only university in Canada that has this software certification center, which is part of our CS department. Well, it's a huge center that has a lot of collaborations with automotive and well, nuclear plants and avionic companies. The only come, here is my software, please analyze it to me to give me some sort of guarantees for certification, right? So it's an industry on its own, being able to analyze your application. Why? Because our applications are not a single 10 instruction program that is just procedural, right? Composed of tens of thousands, if not millions of lines of code. If you remember, I gave you the example of Mercedes-Benz and the F-22 in lecture 1, right? I told you it's millions of lines of code, and based on what is my input, I have many control paths that I need to analyze, which is not very easy. Good. So for that purpose, well, the variability of the execution time is huge. The good thing is that you don't really need to analyze every single instance. Well, you might be able to do different methods to be able to. What I'm looking for from a real-time perspective is not to say, okay, at this moment of time or at this input set, my execution time is milliseconds, right? What I care about the most is, in worst case, my worst case execution time will never exceed, for example, 2 minutes. No matter what is the input, no matter what is the temperature, the variability, the environment, anything, no matter even what other tasks running with me, my worst case execution time is 2 milliseconds. And hence, well, does this really meet my 10 millisecond control loop or 10 hertz control loop requirement or not? If it meets, great. If not, then I need to redesign something, either the hardware or the software. Good. So this is basically the worst case execution time is this instance here, which is the worst possibility. The best case execution time is the minimum execution time in this spectrum. And then the average is basically the average of this number. I have it here or not. So one other good thing about this graph is based on what method you really follow for determining the worst case execution time, you might have different points. What do I mean? For example, there are two big classes into how to obtain this worst case execution time. The example I will just explain to you right now, which is look into all your control paths, analyze it. This is called static time analysis. There are tools that do this, commercial tools and companies that do this. But as I would also say, if the code is very complex, this task is the very tedious. Well, in fact, if I think about, well, toy side terminology, it's an incomplete problem. It's not, in fact, guaranteed that in any, for any program set, I will be able to analyze all these facts, right? If you guys had a compiler, it would be easier to explain because in compilers, they're also related to how to analyze the application different paths. But that's a different story. So I might have an example later on to literally imagine how this is hard. But for now, trust me, this is basically very, very complex. Good. So I might be able to do it for easy tasks, but not for a very complex one. What would be really tasks? Because we still have very complex tasks in every single realistic embedded system. What they do is they do what they call empirical time analysis, or measurement-based time analysis. They say, well, to satisfy those certification requirements, what do? Is I take my task set, I take my hardware, my card, for example, and run it for millions of times with all possible mediums, right? Like think of, you might have heard in the news that Google card has been around in the streets for 10 years right now, collecting data and doing testing, etc., etc. Why? Because you want to test it for different environment setup, well, raining, snowing, clear, different temperatures, different places, different traffic signs, different regulations. So the more testing you do, better test. Right now, I'm literally taking a task, sitting in a room or a desk, and trying to analyze my application. You see, I'm having it in the field, collecting data, analyzing how do I act, fix myself, do it again and again and again. So, and then if I was able to tell the certification authorities that I did run this task for 10 million times with all these input sets, and I'm guaranteeing that there is some coverage that I have covered 99% of the cases, and plus this, I'm adding a safety factor of 15%. This is what we will do in avionics, right? Then well, they will say, okay, you did your due diligence, well, this is safe enough to have it, right? So people go for a measurement based or empirical based because static based is very tough. But the point is that in empirical, you might end up with different numbers based on how many tests you do run, right? This is why you find here, well, this is the maximum observed execution time. Why I call it observed here? Because this is something empirical, right? I run, I measure, this is what I observe, right? And then afterwards, you see here that this, well, my upper bound is a little bit higher than the worst case execution time. Why? Because I add a safety factor just to make sure I also, any case that I didn't account for, I'm already taking it further, right? Most certification authorities ask the companies to add 10-15% safety factor on top of what they come up with. Good. Okay, so again, in a worst case execution time analysis, given a code, I want basically to, well, analyze how many instructions I run, how many cycles they take to run, and then this will be my computation. Doing static time analysis, which is the one that is basically more theoretical, or, well, you don't do it empirically, but rather do it by analysis or verification, you can assume that your static timing analysis tool is a black box that takes two inputs. Your code of the task, which is just simply the software, and the hardware itself, the architecture that is going to run on, which is a model. Basically, you build a model of your hardware. And then the tool itself will run. Run means basically trying to analyze every single batch of the application, assuming the architecture that you are running on, and gives you an estimate of the worst case execution. Good. On the other hand, measurement-based timing analysis, well, based on exhaustive testing or statistical measurements. That's the empirical side of this. If I go to static timing analysis, this is the picture I was telling you, is that you can assume your application or task is split into what we call basic blocks. That's why I said some compiler technology is helpful, because all the compiler analysis is in fact done in splitting your code into basic blocks. Usually basic block in compiler terminology is a piece of code that does not have any jumps, right? You don't, so it's within one function, it cannot span multiple functions. It does not have any for loops, for example. It does not have any if statements or jump instructions. So it basically is a procedural instruction. Why do I call it basic block? Why it's important for me? Because once you know that you never jump out of these instructions, once you enter your basic block, you know that all these instructions in this basic block will be executed sequentially, right? And hence you can estimate it. So I can, well, this is what static timing analysis do, is you split your code into different basic blocks, and then you can see here that there are branches and jumps based on, well, if statements, conditions, loops, instruction, function calls, whatever it is. And then I do analyze all of these and take the worst case path of jumps here, and then come up with, well, an estimate of the worst case section. For example, I look into these instructions. I know that the add takes 1 cycle, multiply takes 3 cycles, memory operation takes 100 cycles. I add all of this up, come up with a number in this basic block, another number here, another number here, here. And then I say, okay, for every single block, I am analyzing separately. Now I want to come up with a number for the whole application. What do? Start from the beginning, take all the possible paths, add everything up along your way. This gives you one value of the computation time, and then take the max across all of them. This is, well, it's a simplistic view of how tools really run. They are much smarter than this, but that's the one way, in fact, to analyze it. Let me stop at that. That's very important. If you didn't get this, please ask, right? Because, for example, in the exam, I might give you an example tool, then tell you, well, tell me the worst case time using static time analysis. And I give you estimates for every single instruction, how much time does it take. So you run by hand in a very simple example what a static time analysis tool might be doing. Does this make sense to you? So I run it in a 2-step. First of all, I divide and conquer. So basically, split my code into basic blocks. A basic block is series of instructions without any jump. Add all the execution times of the instructions, and then come up with that number. Now I come up with an array of numbers for every single basic block. Then the second step is, well, follow all the different paths, and then add things up along your way. For example, one possible path is this one. Another possible path is I go here, but then I come back at the beginning of this because this is a loop, for example. How many iterations do I run? Well, I don't know. Might depend on the index. If I have to take the worst case for numbers, right? And then I add them up, right? Does this make sense? Is there any question? Okay, so you can imagine how hard this can be. If you try to run this example for a very simple, this is a very simple code, like I don't know, 20 instructions, maybe a little bit more, no function calls or for loop statements. This might take you 1 hour, right? As a human being. If I have millions of lines of instructions and, well, thousands of paths, this might take days for a tool to run, right? It's a very complex task to do. Why static timing analysis is in fact generally a big problem. This is why people tend to go for measurement-based analysis. In a measurement-based analysis, well, industry calls this ABTA. You do a lot of measurements. I was telling you, you run it for millions of times. Well, Google car goes into the streets all the time. Tesla is still doing experimental stuff in Tesla owners, right? And then you basically try to do a lot of measurements under worst case scenarios, which what we do is heavy loads, for example, like a severe condition of weather or a lot of traffic along the way. And then take a maximum plus a safety margin. What I told you is 10 to 15%. And this, because this is an empirical analysis, you assume you already run the exact actual hardware you need. For example, a Tesla car, well, you are already using the Tesla. You're using the hardware. You don't need to model the architecture because you are already using the architecture and you collect the numbers, right? And this is a very common practice in industry, again, because of the complexity of static timing. Do you see the difference between both? Statically analyzing the code and measurement-based one? Which one you think is in fact more safe? What do you think?
I guess I can go with that.
Which one?
Static.
Static, yeah, exactly. And why is the case? Yeah, exactly. So you don't depend on this, but rather depend on formal verification, right? So you go through all possible scenarios, then there are guarantees that in fact, analytical guarantees that in fact you are exhausted everything. In a measurement base, well, it depends on how good or how, what is the quality of your inputs, how many scenarios did you cover, right? So one advantage of static timing analysis, if it's possible, is in fact, it's much more safe. And this is why also certification authorities tell the people that if you do static timing analysis, your margin shouldn't be really too high. You can really have you can cut your margin, safety margin, because we are more convinced that basically the numbers you give me is the numbers that really makes sense. Right? On the other hand, for measurement base, it's more practical, less safe, then my margin can be a little bit higher. Okay, one big problem with well, either static timing analysis or measurement based, for example, here, if I analyze this code, we have ignored completely any other task in the system, right? I'm looking into the code of the specific task that I'm analyzing right now, right? This is assuming that the task is running alone in the processor, right? It does not access any shared resource. It's not being interfered by any other task. So, well, that's in fact not very convincing, because we know for now that if I have a multi-core architecture, for example, or even a single-core architecture, that tasks would require access to shared resources like semaphores or critical sections. Well, the behavior of this task will depend on the other tasks running, right? So the problem even gets another dimension of complexity, right? So shared resources are big problems because, well, if you have shared resources, all what we discussed so far alone is void. We cannot really do it. We have to do a little bit more, right? But before we go into how to handle shared resources, because it will take us some time. What are some of the examples of shared resources? I already told you about critical sections or software resources. What else? What do you think, for example, might be shared resources in a Tesla SOC? Well, we have already given the examples of IOs before, right? When we talked about shared resources and scheduling, so accessing certain sensor, for example, the wheel sensor that goes into different tasks in a car, it's a shared resource. Memory, exactly. Memory is another big resource, whether it's a cache or a bus or an official memory. This is in fact one of the most complex shared resources in a modern multi-core architecture. So if we take this picture that we had in lecture 1, which we already discussed. So if you have multiple processing elements, you have tasks that are running here. Well, they share, in fact, a bunch of hardware resources, including a shared interconnect a shared cache hierarchy, well, a shared memory controller and a shared official memory. All of these are shared resources that can cause interference and hence change the execution time of the task based on the behavior of other tasks running in the system. Okay. If you look closely into this one, every single red block here is in fact a source of interference. What do I mean by interference? Basically contention between different tasks running. Because for example, a task running in processing element 0 might want at one cycle to access the interconnect. Like if I go back to this example of code here, maybe at one of the instructions, I might have a load instruction. One of the basic blocks, I have a load instruction, right? Load means I need to get something from the memory. How does really load work in hardware? Well, if I go here, assume our task is running processing element 0. I have a load instruction. I need to go to my private cache first. If it's a mess, I need to send a request in the interconnect that might be get from the shared cache or from the memory, right? So a load instruction would go through, traverse this memory hierarchy. On the same exact cycle, so I have multi-core architecture, another task running processing element 1 might also have a load instruction that also might want to access the interconnect. Well, interconnect is one resource. Can only serve one request at a time. Which one to pick? If I pick the request of task 1, well, I'm delaying this one. Or if I'm picking this one, I'm delaying this one. So there is an induced delay due to this interface. Why do we care about this delay? Because this delay will increase the execution time of the task. I have to account for it when I analyze because I want to make sure in worst case scenario, I will never exceed my deadline. Now the worst case scenario has a new source of complexity, which is the interference. Good. So is the story logical here? Do you have any questions? Okay, so to give you a practical example, assume, for example, we have a dual core system, and then we have a mass level shared cache. Well, here I'm using the avionics technology because I told you before, avionics require you to have partition systems. Every single partition is called the virtual machine, VM. A VM in avionics means, well, let's think of it as a separate core, for example. So it's a core that has its own resources and can be considered as a completely separate core environment. The problem is, assume I have two VMs, VMA and VMB, and assume that VMA running in one of the cores is running a safety critical task, like an airbag task, for example. And by the way, these slides are on Analytical. I see some of you are taking notes, so the slides are really out. And then assume that VMA is safety critical and assume VMB is not safety critical. It's running something like an infotainment unit in a car or an infotainment unit or an informatics task in avionics, for example. And then assume VMB suffers a cache miss, which means if I go to this architecture, assume this is VMB, this is VMA, I have a cache miss here from the non-critical virtual machine. And this cache miss, so think of, I hope you guys covered caches before the end, right? Some sort of, you know what is a cache miss, a cache hit, replacement policy. Yes or no? You know what? Can you give me an example of cache replacement policy, for example? What is even a cache replace? Just let's go one step further. What is a cache replace? Okay, some of you didn't take for the end. Oh, is that true? How many didn't take for the end? Oh, okay. Isn't for game a tool?
Not for
I see.
Yeah.
Oh, yeah, it's not for land. Okay, I see. Okay. Okay, that's good to hear. So, well, thanks for letting me know, because from now on, I will assume minimum knowledge then for the end, right? So if there's anything that I just skip overlook, just ask me live, right? Don't stay silent, just ask questions and I'll go through it. So in a very easy high level, well, we use caching in modern architecture because caches are faster memories that are closer to the processor, right? This is really the essence. Main memory is well, something off a chip that takes a couple of hundreds of cycles to access. So our TDMA, right? All of you guys might have seen a DEM before, right? You can really purchase discrete DEMs from Amazon, for example, right? They are in the range of gigabytes, 32 gigs, 128 gigs. Like something is very cheap but it's very slow in terms of access time. So what modern processors do, if you look into laptop spec, it will tell you, well, I have an 8 megabyte SD cache or a 4 megabyte L1, 4 megabyte L2, and maybe 156 L1. What does this mean? There is a cache hierarchy here. So between the processor and the main memory, I add a bunch of series memories that are faster to access. Why do I do this? Because caching is a very normal technique in even modern ones. If you want to go to the library, then you want to read something about computer architecture, you will go to the shelf and then bring maybe 3-4 books, put them into the table and then sit down, open one. Once you are done, you close it, open another one. It doesn't make any sense that every single time you need a book, you go again to the shelf, bring it and go back and bring it, right? You just basically save your time by bringing a whole bunch of data in one place, and then it's closer to you. It's faster to access. Good. So basically, this is a caching concept. The problem is cache is a smaller capacity compared to DRAM. I was telling you that modern DRAMs are, well, I know my laptop is 32 gigs, yours might be 64, or I know that there are some laptops right now 128 gigs, but your caches are maximum 8 megabytes, right? So something that is well, order of magnitude less in terms of capacity. So most of the time, what you are hoping for, or systems are designed that you will hit in the cache. It means when I have a memory load of store instruction, I'm able to get it from the cache. So it's much faster. Like L1 access latency is 1 cycle. L2 or L3 access latency is maybe 5 cycles. DRAM access latency is a couple of hundreds of cycles, right? So it's again an order of magnitude difference in terms of access time. So again, the hope is that 99% of the cases I'm hitting. But what if there is a mess? If there is a mess, well, I need to go to the main memory, bring this data, and put it in the cache, right? Why do I do this? Because later on, if I need something similar, I access directly from the cache, right? The problem is because cache has smaller capacity, it might get filled in very quickly. So if you want to bring in something from the memory, put it in the cache, you might end up having a full cache. And hence we need a replacement. The replacement means I need to evict something from the cache and put a new line, right? This is why it's called replacement. You replace an old line with a new line. And this was, it's a topic that takes 3, 4, 5, 6 lectures in a lot of papers. There is a lot of complexity in that topic, but this is the essence of the intuition behind the idea. The problem is, and this is what matters for real-time systems, if you had a single task, people, static time analysis, they develop techniques that they are able to say, assume I'm running a single core, single task. Even with a cache hierarchy, people were able to determine by looking into the task pool, which one can be a miss and which one can be a hit, right? So for a single task, I can analyze the number of misses and number of hits. And then hence I have a reasonable worst case execution time. But if it goes to a multi-core with 2 tasks running, here I'm showing you the example, well, here in this slide. I guess I'll keep going back. Here I'm showing you that, in fact, a critical task, in our case, this is an VMA, can be impacted by the behavior of another non-critical task in another tool. Why that's the case? Because of the cache behavior. So let's look into that architecture here and see the scenario that might happen. So I'm saying that VMB, which is I will call it non-critical and critical task, so just to simplify. So this is the non-critical task, this is the critical task. And here we have a shared cache between them. The non-critical task trying to access the shared cache, it doesn't find the data that it's looking for, so it's a mess. It has to go to the main memory, bring the data to the shared cache. Well, the shared cache is full. What do? Well, replace it, which means evict an old line. Do you see what the problem might be? This old line might belong, in fact, to the critical task, which means the non-critical task has evicted a line that was belonging to the critical task on the shared cache. Why that's a problem for execution time? Because originally, if I'm analyzing the critical task alone, I assume this line, if I have a load instruction, this line, it will be a hit in the shared cache. What is the hit? 5 cycle access time. I add 5 into my analysis and then do the worst case execution time. Right now, it's a miss. So it's no longer 5. It's a couple of hundreds of cycles with the DRAM. So the non-critical task impacted the behavior of the critical task, impacted the execution time of the critical task. Good. It's very problematic, right? It's very tough to do, right? That's why in earlier lecture I told you in avionics, they tell you if you want to have a multi-core, this example, you have to shut down one core completely at a time. No 2 cores can be running simultaneously. up until now. They're trying to certify quality. The industry is going through a transition, both avionics and automotive, because of, well, we need multi-cores anyway. There is a lot of tasks to run. I cannot really afford shutting down all the cores. So they try to come up with some guidelines. And we will discuss some of these solutions right now, how to be able to, well, measure this interference, bound it, and hence we can reason about the execution time, even in the existence of measure. Good? So let me stop for a second and see if there is any question. I know that it's a lot of information, right? So you guys feel free to ask, right? Okay. So now I hope I kind of, given that you don't have a question, I convinced you that having shared resources in a multiple system complicates the analysis a lot. So we have to account for. We already have taken the example of a shared cache. There's also shared main memory, shared I/O, interrupts, etc. So many critical sections or shared resources they can have. How to accommodate for this? Well, one possibility to accommodate for this is to say, I'm going to expand my task model. Instead of saying worst case execution time is only related to the computation time of the task, which is what we have assumed in analyzing this, for example, here. All the assumption was that, well, I do all the computations, I measure the time, put it aside, add it up, right? So I'm only bounding the computation time in the core. Instead of this, I need to expand my worst case execution time to also include the access to the shared resource. So we would say worst case execution time now will equal to the worst case computation time. And this number can use the old method of analyzing the task in isolation, looking into the source code, add the numbers, come up with a number. But then you need to add another term to your worst case execution time, which includes the interference from different resources. This interference can be bounded by saying, well, for that task, I measure how many requests in worst case can access that resource. For example, I go back to my code, I count how many load and store instructions I have in worst case. Those are memory requests, which means they are accessing the shared memory. And then for every single request, I multiply it by the worst case possible latency, assuming maximum interference from all other ones, right? And then by doing this, well, I accounted for the shared interference in my worst case execution. Make sense? Okay, so what we're doing is we're extending the traditional model. Instead of saying we only have a worst case execution time, I'm splitting the worst case execution time into worst case computation time, which is basically a guaranteed bound in the core computation. Was add, multiply, divide instructions. And then there is also worst case number of requests for every single shared resource. And then the worst case interference from other tasks. And then again, my worst case execution time will be the summation of it. Good. And this basically takes us to the, well, subsequent topic, which is how to account for different shared resources in modern embedded systems. I will say I will give you 5 minutes break, and then I will switch to the slides. I will also upload the new slides. Okay. Take 5 minutes to refresh your mind, and then we switch to that topic.
That would be great. I can think of all on stuff. I can't make it from the 140. Let's go. Getting it. I should just the one should use that. All time. That's it. So this sort of is there. Okay. So this is so then you have
For the cache part, you mentioned that when there's a full cache, you do the replacement, but you're replacing a line in the same cache as the task that was requested.
Well, not necessarily a line that belongs to the same task.
Not a
But
line that belongs to the- Okay,
Usually it can be any line based on what is the replacement policy.
right,
For example, in most caches, there is what they call least recently used. So they maintain a track of what is the line that was accessed, well, oldest, and then they replace that one.
right.
What task this line belong to? Well, they are agnostic to this, they don't care. And that's really the source of the problem is there might be a possibility that task evicts a line of another task. In fact, if we're able to control that you only evict your own lines,
Right.
we'll discuss this is one of the solutions, in fact.
Right.
If you're able to do this, it's safe. Because I only evict myself, you evict yourself, so I don't impact you, right?
Right, yeah.
That's one of the solutions. We do what we call cache partitioning is instead of having a one big full shared resource,
Yeah.
you partition it into entities and I only access the partition and evict myself
Oh,
if it's full. But right now, out of the box, existing caches don't support this. They
Right.
say is that this is a shared cache. Any line can be evicted based on the replacement policy, including a line of another task, which impacts the interference, like it creates interference, right?
So is that like the industry standard right now? Like it's just.
Well, it's industry standard for multi-core architectures in general systems. But the standard for embedded systems, you say, well, we cannot really accept that.
Right,
Instead, we have to have solutions. But we're going to discuss these solutions. I only wanted to show you the challenge.
right.
Like the challenge is it's very tough to do. How to address it, that's the topic of well, coming slides and next lecture as well.
Okay, perfect.
Okay,
Thank you.
good.
Yeah.
Driving, but. That's the most angry, like, I think we broke the law, she's some kind of. I think we did really deep, they kind of get mistakes. What's the thing, like, places drive up into with the. I have the drive, and you got the fast. We're going. There's a lot of use, so to get things. That's, so this is. But that was something else, whole like decrease. So it's that almost like everything, the whole, I think it is. Four irons in solve with that. That there was. This is that more than this. They goes with adjustment, that's just right. Decision, that's be a question. It was like, it's better answer about. So it's not bad. They bring it along to the news fund. Like, I'm just trying to, it's a part of the apology. It's very massive stuff. Yeah. James, James, what if I speak well, job. Maybe it's like. It's just going on. Just going out. It's slowly going back. Sorry, I said one or two. I think that was not there. It's supposed to be those big heads. It's. You know, I would accept that. You guys don't have favorites. That's what too. This is their visual. I think we. I think you. Where to go? Well, I never took. There's only like a wall, drive the car, like bring. Only one people that seems like I did the sense with the mind, so yeah, that's I spent trouble about first and morning fascinating. Patients, just like whatever, they just fly. Is that so much to the place? That's either 6 or 8. That number is look at brain, something that I found to think you think. So like satellites in the dog and the police out and all. I like how bad I make them did it. It's something drastically in the morning, but did it. And what you're. Walked up. Absolutely. You bring it up to absolutely burn. Yeah. No, you're good. It's a life. Just like earlier, that's a very it's still building, but the ocean. Universities that was from press actually from. But it's free. That's the point. Anything else that we should do about it's one of
So as we said for the break, this takes us to discussing different shared resources in modern multi-core embedded systems. We'll start by the interconnect. Well, first of all, what's an interconnect? What is a multi-core architecture? If you look into, a chip design, the problem is we have what we call in the most modern multi-core platforms, including the ones in your laptop, in your mobile phone, in a car, in avionics. Doesn't really matter. We have what we call a bandwidth fault. What does it mean? It means that given the huge amount of data we need to process, for example, from cameras, from sensors, there's a lot of data that need to be stored and transferred and processed. And we are no longer limited by the core running frequency, but instead by the how fast we can transfer data and store it, which is basically what we call a bandwidth. Bandwidth is simply how many bytes are being transferred per second. Good. And we need a scalable communication between cores in a multi-core system and between memories. How can we provide this? And as we have seen also in the example, the delays that are suffered when accessing a shared resource, including a shared interconnect, this will impact, well, memory access delay, this will impact the task force execution times, and they have to account for them. Why? Because interconnect links are also shared resources, and then tasks will suffer interference from each other. They will contend to access the shared resource and delay each other. There are multiple types of interconnects based on what platform you are using. In a very simple embedded system, example in our SMU, we have already discussed 2 types of buses, if you remember, an internal bus and the external bus, the nature of the IO, right? So in a simple embedded system, we have what we call a shared bus. What is a shared bus? Well, a bus is a form of an interconnect, but it's a broadcast medium, which means every single one in the system, every single core, every single IO controller have access to that bus, right? So it's a unified single resource, and each data transaction interferes with every other transaction. So because I cannot really send 2 transactions simultaneously on the same bus, a bus is only one unified view. It's a series of wires that are seen by every single one. It cannot hold 2 transactions at the same time, right? And for that reason, it's not scalable. So it's very easy to design. So it's very common in low-end systems. But it's not scalable because they cannot really have a shared bus amongst 16 pools or, 64 IOs. Why? Because it limits the bandwidth a lot, right? Assume that you have a shared bus and you have 64 IOs, including sensors, SPI, I2C connection. If any single time you are sending something from the I2C controller to the processor, the remaining 63 IOs cannot really send something, right? So you limit your current less than the IOs a lot by the shared bus. There is a little bit more advanced interconnect. It's called the crossbar. Well, in a crossbar, instead of having a single shared resource, you have an in and M out ports. This is, by the way, very common in communication system and switches and routers. You might have seen it before in one of the courses. But the idea is you have a matrix of buses instead of a single bus, and they have an in input port and M output ports. And then if you want to connect from one input port to an output port, you basically set some switches to create a path, right, from the input to the output. As you can see right now, multiple transactions can go in parallel. For example, I can go from 1 to A. If you think I go through all these wires, simultaneously, I can go from 2 to C because they never interfere with each other, right? They don't share any single link. Simultaneously as well, I can go from 3 to B, right? So I can have multiple transactions on the same cycle without interference. So crossbar is more scalable, right? But as you can see, the cost is that in fact you add more hardware resources, right? Requires more implementation. Each input is connected to each output, usually employs virtual input buffers, because you have buffers here that you need to see how much data to be transferred. For example, I have a red buffer that goes to a red data, then a blue one and a green one. The problem is if I have so many inputs and outputs, a very large system, this is as if you have a dedicated bus for each. It's a point-to-point connection. So there's a lot of hardware over, right? For that reason, even if it scales better than shared bus, it's not generally scalable because not because of latency or bandwidth limit similar to the bus, but instead because of the hardware cost. Good. And then we have the most advanced thing, or the general thing, which what we call network connection. In a network connection, this is, by the way, what we have in most modern systems, including Tesla, as you've seen, including modern FPGAs from Xilinx or Altera/Intel, including Xyron processors. Like network connection are solving a lot of scalability issues. So right now, I'm generalizing the system, mimicking. You guys might not be aware of NOx or network connection, but you are aware definitely of general networks, like for example, the internet, right? What you do is that every single entity is, well, a node in it. For example, at home, you have a router, which is your gateway to the general network. Internally, you have your internal network. But then if you want to go to the actual network, you have to pass through your router, right? And for that, what the same technology happens, but within the chip itself. Every single processor or every single memory or every single I/O is considered a node. And this node would have to go through a router or a switch to connect to the actual network. The good thing about this is that I can manage a very complex traffic without interference. For example, if this processor wants to talk to that processor, it will go here. While if this processor wants to go to that processor, it will go through that link. You only suffer interference when you share links, right? So that's good. The problem here is that this is a little bit complex to design the router because it has to be very general. It has to be very general in the sense that based on what are my inputs, I need to route them into different destinations. And also I want to minimize interference, right? For real time. I can have, well, there are different topologies in network connection. But what I'm showing you here is the most general one. But there is what we call a ring, which, well, ring is very common in Xeon Intel processors, for example. Which is, well, instead of having this complex interaction, I only have a ring between all the processors, right? So it's a circular bus, in a sense. And we can have a tree, we can have a mesh, 2D mesh, a torus. So there are multiple network connection architectures. Not the focus of that course. One, like I just to convey the message further to you. This is more again a topic of an architecture course, but just to understand the essence of network connection. Contrast this to off-chip, as I was saying. Well, there are different advantages and disadvantages or pros and cons. In an off-chip network, for example, well, it's in fact a synchronous network. What do I mean by this? What you do is completely independent of the other homes, as in the internet or other countries, right? Something that's completely federated, everyone is doing its own thing. There is no need for synchronization. Why a network chip? All of this is running the same chip, being fed by the same clock tree, right? The same clock. So in that case, all of them are synchronized. So synchronization is much easier in network on a chip because you are talking about a very small chip that is, 1 millimeter by 1 millimeter might be like 1 centimeter by 1 centimeter, and then all of them have a shared clock, so they are all synchronized by nature. The link width. Well, wires are relatively inexpensive in on-chip networks. Why? Because it's a very small distance, which means I can really have a wide length. We have discussed this already in our lecture when we said the internal buses are usually using parallel technology. Remember, we have serial interfaces versus parallel interfaces. And we said parallel is very common in the bus on the chip between the CPU and the controller. And we give the example of the AXI bus. We said one reason for this is you are already on chip, so the wires are very short, and hence you don't need a lot of synchronization. It's very cheap to have it. While if you go open chip, well, you better go serialized, right? So this is what we are writing here. In many other hands, many off-chip networks, PCIe, well, they are using serial communication, as we discussed already. Buffers also are relatively inexpensive for off-chip. Like in your router, in fact, you might be able to see this in the spec as well. Some of them are software configured, but usually the buffers in your router are very large buffers, because usually internet packets are also very large. But because basically a router is an HP in its own, it's very large, so that the circuit can allocate enough capacity for a buffer. On the other hand, for a network on a chip, we're talking about a very small real estate, like it's again 1 centimeter per centimeter. Buffers are very expensive. Memory in general is very expensive, and hence I cannot have a very large buffer in network on a chip, right? Yeah, as I was saying, the buffers in the network on a chip is the main cost, and hence we try to minimize it. So wires are cheap, but buffers are expensive in the network on a chip, right? And so this drives many of the design aspects of network on a chip. So this is basically a whole introduction about different interconnect architectures. For simplicity and well, to focus on more on what we focus on in this embedded system course. This is not an architecture course, but an embedded system course. We need to focus more in analyzability. And because buses are much more common in hard real-time systems, we are going to focus on bus architecture for real-time embedded system analysis and see how does it work. As we have seen in this picture before, well, a bus is simply a shared one big resource that goes through from all the pools. Here we have a pool with some private caches. Then it acts as a shared memory bus that goes to the shared cache and then the shared memory. Well, because we need predictable bus, so we need an arbiter that decides which pool can access this bus at any cycle. Most of the discussions in real-time analysis are concerned with this arbiter. How do I bound the latency? If any request. So remember, what is our bigger picture? Our bigger picture is try to drive worst case execution time. To be able to, maybe I should write this. So to be able to drive a worst case execution time, remember we had this equation in the previous slide. So we have worst case execution time is equal to worst case computation time plus number of memory requests multiplied by the worst case latency any request can suffer upon accessing the shared resource. We said this we can obtain from static timing analysis, similar to what we discussed, but this is the new added delay because of shared resource. So if I'm talking about shared memory bus, I need to see how many total memory requests I have in the task and multiply this by the worst possible latency that a request can suffer. Why worst possible? Because I care more about worst case execution time in real-time analysis. Good. So all of the aspects of analyzing the bus is to drive this value here, worst case latency of a single request. Good. So this is our main focus. This is the target of what we are looking for. In doing so, there are several predictable. Well, what do I mean by predictable? So if you look here, do I had that term somewhere here? Yeah. So predictable architectures for interconnect. What do you mean by predictable? Predictable means the bus itself and the arbiter gives you a way to be able to drive this value. Well, is there a possibility that I'm not able to drive a worst case, an upper bound of the latency I suffer on the bus? Well, in reality, yes. In most your laptops, in most average case scenarios, there is no bound, as I was saying earlier, which means our architectures in general are not predictable. You cannot really drive a bound on how much delay you can suffer. Why that's the case? Because the delay will depend on all the other status of the system, the operating system, the applications that are running, what arbitration policy you deploy. For example, in most laptops or most average case high performance architectures, I have what we call a fixed priority, first ready, first come, first serve arbitration, which means I do a lot of reordering. In other words, one request can come to the bus in our laptop and wait for hundreds of cycles without being serviced. Why that's the case? Because it might be a lower priority. It might be because it's not ready right now, so it has to wait a lot more, right? So one of the tension we have already discussed, one of the key aspects of embedded systems is how to identify the aspects in modern multi-core architectures that lead to unpredictability and provide something different that is predictable, right? So the idea is that we want to discuss different predictable arbiters that lead us to be able to bound worst case latency. If I'm not able to bound worst case latency, what's the impact of this? Well, if this value is not bounded, this value is not bounded, right? So that means there is no guarantee that this value will be less than or equal to the deadline. So I lost basically the timing guarantees of the system. I cannot really have the car in streets. I cannot guarantee my safety critical healthcare device. So there's no guarantees, right? So the whole aspect of, well, one of the big aspects of the course is, am I able to bound the worst case execution time to be less than the deadline? And this part of the course, like this lecture and the coming lecture is, okay, how do I bound this? We already discussed worst case competition time, static timing analysis, measurement based, and we want to spend some time to discuss this interference additive latency, right? Good. If you miss the big picture, you will not see really what we're trying to do here. Good. So again, if there are questions, please let me know. One of the predictable and very common embedded system arbiters is time division multiplexing. And it's also very common in communication systems as well. So I would assume you might have discussed TDMA in one of the communication courses. So why TDMA is easy to analyze for embedded systems? Because, well, it's a static scheduler, right? You already know the schedule beforehand. In a simplistic view, each core gets its own slot. And usually this can be very easily implemented using a lookup table. Because it's static, I have a lookup table that says, well, slot 0 core 0 is running. Slot 1 core 1 is running, etc., etc. So you can see here an example schedule. I run C1, then C2, then C3, then C4, 5, 6, and then C1 again. Why TDM provides predictability and composability? Okay, so this is a new term that I'm throwing on you right now. We already discussed what is predictable, which means the ability to be able to bound this value, worst case latency for request. What do I mean by composability? So let me take a minute to explain both, and then let me know if you have questions. So we already had this variability of the execution time, right? Graph. And then we said there is a worst case execution time value here. There is a best case execution time value here, right? If I was able to drive this worst case execution time, I say that my system is predictable. Why? Because I can drive my worst case execution time and I can decide whether it exceeds the deadline or not. On the other hand, if for example, especially in hardware buses, in interconnects, instead of talking about execution time, now I'm talking about latency. So there is a worst case latency, there is a best case latency. If there is a bus that in fact does not induce any variability at all, which means in fact my best case latency is equal to my worst case latency is equal to my average case latency, which means I can really, well, instead of having this graph, I reduce it into a single point. Worst case latency equal to best case latency equal to average case latency. I call this bus composable. Well, how can I achieve this? Well, you can achieve this by ensuring that no matter what's happening in the system, you always a request to your bus, for example, suffers exactly the same latency. I'm claiming that TDM is in fact doing this, and I'll show you how, right? So you can understand composability by looking into TDM very easily. But the idea is, I hope the idea is clear. The difference between predictability and composability is, in composability, your best case execution is equal to the worst case execution is equal to the average case execution. It's in fact a single instance, right? It's a single value. In predictability, there is a variability, but you're able to bound the variability, right? In that sense, and this is a bonus question, is every predictable system a composable system? Or every composable system is a predictable system? What do you think? What is the superset? If I want to draw a circle of composable and predictable systems, what do you think is, if I have one of them, I would by default have the other? Yeah. Exactly, thank you. Every composable system is a predictable system because by default, a composable system, the worst case is equal to the best case is equal to the average case. So you know what is the worst case. And we said by default, once you know what is the worst case, it's predictable, right? So we can really say, if I have a set of predictable systems, there is a subset of them that is composable. So every composable system is a predictable system, but not the other way around. Good. And we will see this right now in TDM and round robin and other arbiters. So what I'm saying is that TDM is both predictable and composable. Why that's the case? Well, in TDM, I give every single core a slot, regardless of what other cores are doing. If there is a core that does not have a request, or the core that have a request, it doesn't matter for me. For example, core 1 always gets this orange slot. Does it care what the other, does it care about what other cores are doing in their own slots? No, I always have my own orange slot, right? So what would be my worst case latency? What do you think? What is the scenario that will lead a request from core 1 to suffer the worst case latency? In that scheduling, I'm already showing you the TDM schedule. I want to bound, again, go back to our big picture. I want to drive this value. So I want to drive what would be the worst case latency for a request from core 1. What would be that latency? Maybe I even give you a number. Assume that every slot takes 10 cycles. Can you give me a number for the worst case latency that can be suffered by a request from core 1? 50, 50. So 1, 2, 3, 4, 5, 6. So I'll assume you said 50 because you assume you are right here, right? Yeah, well, that's very close. So I would say maybe there is a possibility that you just arrive one cycle after you slot. Yeah, so that's a small detail. So basically, the way TDM works is that at the beginning of the slot, I look into the code. If you have a request, I serve it. But that's at the beginning of the slot. If a request arrives just once cycle after the beginning of the slot, it's not being served. And in that case, you have to do, right? So the worst case is not that you arrive after you miss your slot, but instead, you arrive after one cycle of the beginning of the slot. So I would say, well, that's a very close answer. Thanks for that. And I was missing a bit of a detail, so it's not your fault. But the worst case here is basically 60 cycles. Well, to be very accurate, it's 59, 60 minus 1, right? But just to approximate 60 cycles. So, okay, good. This is the worst case. Will this worst case be impacted by whether C2 or C3 or C4 have requests or not? What do you think? If every single core here have a request, will C1 latency become larger? Worst case, become larger than 60? No, in reality, right? In other words, if C2, C3, or C4, all of them don't have requests, will this make C1 run faster? What do you think? TDM? No, as well, right? Because what TDM does is if a slot does not, if a core does not have a request during its slot, it remains idle. Just it's no one is using it. So why is composable? Because TDM, if a core does not have a slot, if a core does not have a request in a slot, the slot remains idle. No one is using it. Why this feature is here? To ensure composability. My delays as a core will not be impacted by whether other cores have requests or not. Because whether they have requests or they don't have requests, their slots are idle anyway. So I have to wait for my delay anyway, which means my latency equal to my worst case latency equal to 60 cycles all the time, right? Good. Okay, so some of the advantages of TDM is predictable because again, we were able to, the real framework was able to drive a worst case latency, it's predictable. So each core can suffer a maximum interference of one request from each other core, which is basically the worst case latency. It's composable because the worst case latency is enforced by runtime. The actual latency is the worst case, as we're discussing right now. It's fair. Why? Because I'm giving every core one slot, right? So each core is getting the same service. So it's fair scheduling. And it's very easy to analyze because if I want to drive a general bound TDM, if I have n cores and the access time for the bus is S cycles, for example, I can very easily say my worst case latency is equal to, well, your friend here was able to drive 60 as the worst case latency. Why that's the case? I told you that the slot width is 10 cycles. I'm suffering 6 slots, so 6 by 10, so 60 cycles, right? What if I have n cores? Well, it's 10 by n, right? If I have 100 cores, it's 10 by 100. What if instead of being 10, I'm just generalizing it to be S, which is the execution time of one request? Then my worst case latency, analytically, if I want it to be a function of the slot width, so I'm assuming here that this is S cycles, and the number of cores is n. So my worst case latency in TDM, just simply n multiplied by S, right? So we just analyzed the worst case latency of TDM in 1 minute, right? It's very, very easy to analyze. Does this make sense? Okay. So some of the disadvantages of TDM. It's not requirement aware. What do I mean? Not every single core would have, well, we said it's fair, right? Which is something that is good. If you look here, well, it's fair scheduler. Every single core gets the same number of slots, but those cores are running different tasks, right? Every task would have its own requirement, its own deadline, its own number of memory requests. So why I should serve all the cores in a symmetrical fashion if they have different requirements, right? So fairness is not always good. So that's the bad side of fairness, which is, well, it's not requirement aware. It doesn't take into account what are the task deadline or number of requests or required worst case latency. And it's not also criticality aware. What do I mean by this? Remember we said our systems are general mixed criticality, which means some cores are more important than others. Some tasks are more important than others. If I run in a bus and there is an airbag control task and there is an infotainment task, I cannot really serve both the same way, right? So TDM is just serving every single core with one slot, regardless of what is the criticality of the task. So it's not also criticality aware. Another bad or cons of TDM is it has a wasted performance. Why it has a wasted performance? This is the bad side of composability. Because we said if a core, if you look here, it's composable because, let me see. If a core does not have a slot, if a core does not have a request, the slot will remain idle. But, well, this is really a waste of the bus. If that core does not have a request, other cores might be having requests. So why am leaving the resource unused during that slot? Well, this is good to enforce composability, but it's bad in terms of performance, right? So it has a wasted performance. So here I'm giving you an example. If core 3 does not have a request during its slot, I will waste, well, the S cycle, the 10 cycles in our example, without being used at all, right? If I wanted to use it, well, in fact, I can make C4 execute here, C5 execute here, and I finish early, right? So my performance can be better, but TDM is not doing this. Is there any question about TDM? So those advantages and disadvantages take us to the next very common arbiter in real-time systems, which is round robin. Unlike TDM, which is static, has dedicated slot per cores, round robin is dynamic. What does it mean? It means that, in fact, I serve requests in a cyclic fashion. So I start by core 0, for example, see if it has a request, serve it, then go to core 1, core 2, core 3, etc. Once I'm done, I go back again to core 0, right? So this is what I call round robin because it serves cores in rounds. What about the good things? Well, it's predictable. Why? Think about what do I mean by predictable and able to drive a worst case latency. Can I drive a worst case latency in round robin? Yes, in fact, because in worst case, I come, this is not my round, I have to wait for all the other cores to execute. And hence I need to wait for a bounded latency. I can redrive a latency, which in fact we can do here. So can someone try to think of, well, with this behavior of round robin, what would be the worst case latency if I assume one request takes S cycles and I have N cores? We already said that the TDM worst case latency is N multiplied by S. In round robin, what do you think would be the worst case latency? And that's another bonus question. If you think of how round robin operates in this cyclic fashion, how to drive a worst case latency, think of the worst scenario, right? What would be the worst scenario in round robin? Yeah. Well, this is an answer that I was expecting, but it's not completely correct. Think of what might be the subtle difference between round robin and TDM. Well, TDM, well, I was also expecting your friend answer here for TDM. So for TDM, we said, well, you might think my worst case is that I arrive here. But in fact, no, in TDM, because it's a static thing, you only account at the beginning of the slot. And the worst case, you arrive one cycle after. But round robin is a dynamic schedule. There is no concept of slots. There is no concept of lookup table that you have to go to. Every time it looks into what core is the top of the queue and which one need to serve. Right? So for example, okay, I will give you one example. Assume to be the same, it means that I have to arrive here, correct? One cycle after. But in fact, if I arrived here, round robin decision. So, well, let's discuss this in a bit of a detail. TDM decision here at this cycle at the beginning of the slot was this is core, go to the lookup table, get up the core of that slot. This is core one slot. Does core one have something to serve? At this moment, no, right? Because you only look at the cycle. So you just wait, make it idle. And then my request arrive one cycle after, but I have just wasted my opportunity, right? This is the decision of TDM. What would be the decision of round robin? In round robin, my decision at this cycle would be look into which core is in the top of the round right now, right? So I have some sort like of a sacral queue here. This is how round robin is in reality implemented. I have all the cores. I look into my top of the, and I maintain a pointer for the current round. This is C1. Does C1 has something at the beginning of this slot? No, right? Because the request arrives one cycle after, right? Well, what round robin would do? It will not waste the slot like TDM because it does not have a concept of slot. It will go to the next request afterwards. So it will serve C2. And then it will serve C3, 4, 5, 6. And then it will go back again where C1 is at the top. So C1 request will not have to wait for the slot because the actual schedule right now will be C2, C4, C5, C6, C3. Why I'm having them in that order right now? Because maybe this is how they arrived. And then I will go back to serve C1 again, right? So because round robin is dynamic, I don't waste the slot, and hence I only need to wait for all the other cores to get serviced, right? If I don't have something during my own slot, this slot goes to another core. So it saves me one slot, right? So what would be the worst case latency then, if that's the case? Instead of NS, yeah? N minus 1S, exactly, thank you. So it's N minus 1S. Good? This makes sense? So round robin has a slightly better worst case latency. But the main point is I was able to drive a worst case latency. What does this mean? It means round robin is predictable, right? This is our definition of predictability. It's also fair because every core gets one slot in a round, right? It's easy to analyze because again, we analyzed it in a couple of minutes. Easy to implement because I told you that it can be implemented easily using a cyclic queue, right? One good advantage of round robin compared to TDM is dynamic, right? It's a dynamic schedule. It does not have this concept of static waste the slot being idle. No, I always look into what is next, what is next, what is next. So my behavior will depend on the current scenario of the cores. Well, that's a good side of it. what do you think might be the bad side of being dynamic? Something that TDM might have, but round robin will not have, based on this dynamic behavior. Well, TDM is static, which is bad in terms of performance. Round robin is dynamic, which is good for performance. But what might this impact us? What do you think? What might be the bad side of being a dynamic schedule? Yeah. Yes. Yeah, that's correct. But that's, well, round robin is also easier to decide because you already have the circular queue. So it doesn't take a lot of decision making, right? So it's easier to, but there is one thing related to real time, not to the execution itself. So if you think about TDM discussion, we said it's static, which has the problem of performance, but it gives us what? Gives us, yeah, composable, right? TDM is composable because I waste the slot. Why TDM? Well, TDM is not stupid. Like there are many systems. In fact, avionics are deploying TDM a lot. They don't do this because they are stupid that they want to waste performance. They want this because they want the system to be composable, right? Round robin is dynamic. What this comes at the cost of right now, my behavior will depend on the other cores. For example, core 1 will suffer the n-1s if all the other cores have recursives. What if what if C4 or C5 don't have recursives? Will C1 finish earlier or will finish later? What do you think? Will finish earlier, right? Because if you look into the circular queue, it does not have to wait for C4 or C5. So I take less latency, which means my worst case latency is not equal to always my actual execution latency. There is a variability. This variability will depend on what the other cores are doing, and hence I'm not composable, right? So round robin is predictable, but not composable for that specific reason. Good. Good. So, well, in addition to this, well, because TDM, so round robin similar to TDM is fair, so it's also not requirement aware or criticality aware. But the bad side of being dynamic is not composable, as we're discussing right now. Good. So here I'm giving you an example of, well, if like taking exactly the same example we had in TDM, if C3 didn't have something here, in TDM it remains idle. But if I go to round robin, if C3 does not have something here, well, I will serve C4, right? It will really depend on what version of, well, my apology. If C3 does not have something here, I will serve C4, but then shift everything afterwards, right? Good. There is another version of TDM that we call it work conserving TDM. So, well, work conserving TDM is different than round robin. It's exactly TDM, except that it does one slight difference, which is it does not maintain idle slots. It doesn't leave the idle slot idle. Instead, if there is a core that does not have something during its own slot, it logs into the subsequent core to see if it has something, right? So here in this example, C3 didn't have a request during its slot. Well, the arbiter will look into the subsequent core. It's C4 in our case. Does it have a request? Yes, it has a request. The main difference between work conserving TDM and round robin is that in round robin case, if I serve it C4 here, I will serve C5 here because it's dynamic. So I go into order. In work conserving TDM, no, I still maintain the concept of slots. So even if C4 was served during the C3 slot, this is considered a bonus. C4 would still maintain its own slot. Good. Again, the problem here is that work conserving provides good performance compared to traditional TDM, but again loses composability. So now, just to make sure if any of you is lost, let's have a very particular example and list all the schedulers together. Good. And I want to consider, well, TDM wise. Why it is that's interesting. Okay. Okay, so in this example here, and I hope even if I lost you in any of the even if I lost you in any of these theoretical explanations, You can, in fact, you still have a chance to understand this by looking into the example. Okay, so let's have the example together and then we'll conclude the lecture. I list all the four, well, we already discussed TDM, work round robin, work conserving round, TDM and then round robin. I have here two versions of round robin, I will send it to you. But let's have an example. Example means what? So you have an arrival instance of requests from pools and you want to schedule them. So here what I'm assuming is that at this time, usually in real time, you use the down arrow for arrival. So there is a request from pool 1, pool 2, pool 4, another request from pool 4, 5, 6. And then C3 arrives one cycle after it starts. Let's see how each schedule will behave. Taking TDM as an example, I start by, well, at the beginning of the pool 1. Does pool 1 have a request? Well, yes, because the request arrives at the beginning of the spot. Then I will serve C1. Once I'm done, I will go to C2. Does C2 have a request? Yes, then serve C2. Then at the beginning of the slot of C3, does C3 have a request? No, because the request arrived one cycle later. Well, what TDM will do? Leave this slot idle. So as you can see, during this blue slot of C3, nothing is being done. I waste the whole slot. Then at the beginning of core 1, core 4 slot, does core 4 have a request? Yes. What do I do? Then core 4. Then C5 the same thing. Then C6 the same thing. Once I'm done, I start a new round, a new scheduler, a new period with TDM. Well, at the beginning of core 1 slot, does core 1 have anything? No, I already served the core 1 request here, so I have to remain idle, right? Core 2 also does not have anything, and I also remain idle. Core 3, yes, this request from core 3 is serviced here. As you can think, core 3 here is suffering the worst case, right? So it arrives one cycle after the beginning of the slot, and it has to wait for the next TDM value to get service. And then core 4 had another request here for a server here. Make sense? Good. So that's TDM. I believe that's easy enough. What about work conserving TDM? Well, work conserving TDM shows us that it's better in terms of performance. Let's see how. At the beginning, again, C1 has something, I serve it. C2 has something, I serve it. Here, C3 does not have any. Work conserving TDM does not make the slot idle. Still, look for the subsequent core. Does core 4 has a request? Yes. Then serve it. Once I'm done, I go back again to the core 4 again. This is core 4 slot, right? It's a static schedule. If core 4 gets serviced during core 3 slot, it doesn't mean that core 4 will lose its own, right? It will remain the same. At the beginning of core 4 slot, does it have a request? Yes, because core 4 here had two requests. One of them is being serviced here. There is still one remaining request. So I serve it. What about core 5? Yes. What about core 6? Yes. Then at the beginning of core 1 slot, does core 1 have something? No. Does core 2 have something? No. What does core 3 have something? Yes. Then I serve it during core 1 slot. If you look here, it's very clear that work conserving TDM is much better in performance, right? Here, how many slots did I have? 10 to serve all the requests I have, because I ended up with having 3 wasting slots. Here, how many slots did I take? 7, right? So I saved the 3 idle slots. I saved them in work conserving.
So about work conserving TDM, does it always have to be a subsequent slot? So for example, what if the third was C2, but it's still wait for the next cycle or serve at the same reason?
Yeah, you mean here C2 also had another request?
Yeah, but more in place of C4.
Yeah, I guess the general question is, what is the order, the cores that if there is an idle slot that work conserving TDM is scheduling to, right? And this appears from the second example here. You always start from the subsequent one. So here at this point, this was core 3 slot. So I start by asking core 4. If it has something, I take it. If not, then I go to core 5, 6, then back again to 1, and then 2, right? Well, this appeared here because here this was core 1 slot. Core 1 does not have anything. I could check core 2 does not have anything. Then I check core 3, core 3 has something, right? So you always go to the order of the lookup table, right? In round robin, here I have 2 versions and they are slightly different. So let's see how this happens. So again, follow the example cycle by cycle. At the beginning of core 1, assuming that our round robin order is always core 1 to core 6. Core 1 has something, serve it. Core 2 has something, serve it. Core 3 does not have anything. What do I do? Well, just look into the subsequent core. Core 4 has something, serve it. Instead of, well, maintaining core 4 slot, round robin does not have a concept of slot. It has a concept of rounds, right? So once core 4 is served, it goes back again to the back of the queue, because that's the circular queue, right? So you serve core 5, then 6. Now core 3 gets service. Why? Because if you want to visualize this, think of what would be the rounds of round robin. So I have core 1, core 2, core 3, core 4, core 5, core 6. And this is my round robin order right now. I start by core 1, I serve it. Then I put it at the back of the queue. And then I go next to core 2. Core 2 has something, yes, serve it. And then put it in the back of the queue. And then move my pointer. Core 3 has something, no. What do I do? Well, let's assume right now I put it in the back of the queue. And then I go to core 4. Core 4 has something, yes, serve it, take it out, put it back, move your pointer. Core 5 has something, yes, and then core 6 has something, yes, serve both, and both back at the beginning, at the end of the queue. Now, my pointer is here. Does core 1 has something? Well, no. So I basically take it out, put it at the back of the queue. Core 2 also does not have something. Now core 3 has something, so I serve it here, right? This is supposed to be not core 1, in fact, this is supposed to be core 4 request, right? So that's my bad. And I should fix that. And in fact, this is supposed to be, yeah, colors don't matter for now. Okay, so why I'm saying that there are, excuse me. They might also want to add this as core 4. So why I'm saying that there are there are two versions of round robin. Well, because in reality in industry, there are two different implementations that are possible. And these two implementations will differ based on the following question. What do you do with a core that currently has the pointer as the top of the round robin order, but does not have a request? One possibility is, I don't care, I put it back to the queue, what we have done. Another possibility is, well, in fact, no, I'm going to keep it with its own slot. So I only bought in the round robin order the ready requests, right? So maybe it's better to show you in a slide. What do I really mean by that? Okay, so the first implementation we have discussed is that in my circular, so round robin version 1, in my circular round robin queue, I always put all the requests, all the cores in my queue, right? Whether they have something or not. And then I go into the order from the beginning. C1 serviced, C2 is serviced, C2 is serviced, C2, C3 does not have something, so it goes back, and then 4, then 5, and then 6, and then 3, and then 4. Right? This is what we have done already in the previous slide. This version of implementing round robin assumes that you always do round robin arbitration among all the cores, regardless of whether they have ready requests or not. Another possible implementation is, well, no, I'm only going to arbitrate between cores with ready requests. So I don't push into this circular queue a core unless it have a read request. So let's see how does this really differ. So in the second version, I'm saying, well, in fact, initially I don't have all the cores in the queue. I only have the ones that have requests. Good. So how does this really happen? Well, I go back to my example. I see the sequence here. So I have C1, have a request, C2, C3, C3 does not have something, and then C4, and then C5. Good. So these are the one, this is C6. These are the cores with requests right now, right? And then I start servicing them. C1 has a request, serve it. C2 has a request, serve it. C4 has a request, serve it. Put in mind that at this point, C3 is not even in the queue, right? So I don't even say, well, C3 does not have something, take it out, book it, put it back at the queue. I don't even consider C3, it's not in the circular queue. When does C3 arrive? It arrives slightly after the beginning of the slot, so it arrives here. This is C3 arrival. Once this arrives, so if I look into how the status of my queue looks like, once I picked C1, my queue here is C2, C4, C5, C6. Here, it's I picked C2, so it's C4, C5, C6. Here, I serviced C4 already, so it's C5, C6, but then C3 has arrived, right? But in fact, there is one slight difference, which is C4, once you take it out, C4 had a second request, if you remember, right? So I should put C4 back again, right? So at this point, C4 is taken out of the queue, but it put it back, right? So I put C4 back here, and then C3 arrives afterwards. This is a slight difference in order than what we had in the first implementation. So if I want to serve, I serve C5, and then C6, but now I serve C4, and then C3. Why did this happen? Well, because C3 didn't in fact arrive before C1 is being baked and put back to the queue, right? So these are the two possible implementations. This is round robin version 2. So again, what is the big difference? In the first one, my circular queue includes all the cores, regardless of whether they have requests or not. In the second example, I only push into the circular queue a core that has a ready request. Good. And if a core has two requests, I only push it once. Once the first one is serviced, I push it back. Good. Okay, so let's stop here and we can continue next time. Thanks, everyone.
Professor Ebel.